Hello. In this video, we're going to look at some interesting applications of exponential equations in the form of compound interest. So let's say Jimmy invests $4,000 in a savings account with a fixed annual interest rate of 6%. What will be the account balance after 1 year? Now, interest is sort of like a basic percent. You could think of it as just an increase. If you have $4,000 and you want to increase it by 6%, you could multiply it by 0.06. That's going to give you $240. And you add that back to the 4,000, giving you $4,240. Now, just as a shortcut, if you're trying to increase something by 6%, instead of multiplying by 0.06 and then adding back the original, you could take the 4,000 and multiply it by 1.06. The 1 stands for the 4,000 that you're keeping in the account, and the 0.06 is the 6%. And in one step, that'll give you $4,240. Okay, seems simple enough. But what about after 2 years? What would the account balance be after 2 years? Here's where things get a little interesting. One group might argue, well, the interest was $240. So 1 year is 240. 2 years, I guess, would be 480, right? You just do 240 and then another 240. So our total would be 4,000 plus 240 plus another 240, giving us 4,480. But another group might argue, well, when we do the interest, we're multiplying by 1.06. So instead of doing all this adding, why don't we just take the 4,000, multiply it by 1.06 for 1 year, and then 1.06 for another year. When you do that, something interesting happens. You get a different number, 4494.40. So if you look at that, the difference between these two is, not huge. It looks like it's only about $14, but this second option gives you more. And you might ask, well, why are we getting more in this option than in the first one? Well, in the first one, we're just getting $240 each year of interest, but that's not the most accurate way of calculating the interest, because in the first year, you have $4,000 in your account, and you get $240 of interest. But in the second year, you have $4,240 in your account, because your account has the original money, and you've left the interest in. So when you do 6% of that, you get $254.40. So if you notice, your interest has gone up. The reason is that you're getting interest not just on the 4,000, but you're also getting interest on that extra 240. In other words, you're getting interest on your interest. This is called compound interest, and it helps you get more interest, which is a good thing if you're investing, because more interest, more money, this is definitely something you want. So what if we let it keep going? What if instead of doing 2 years, we do 5 years? Well, we would take our $4,000 we had to start, multiply it by 1.06, 1.06, 1.06, 1.06, and 1.06 for 1, 2, 3, 4, 5 years. But at some point we'll realize that if we have 5 1.06's, we have 1.06 to the power of 5. Think about it like exponentials. So we have 4,000 times 1.06 to the power of 5. And that gives us a total of $5,352.90. Now, obviously, that's a good chunk of money. We've made over $1,300 in interest by not doing anything, just leaving our money in the bank. It's kind of fun. But additionally, we want to notice how this formula is working. We have this $4,000 in front, which is sometimes called the principal. This is the amount of money you start with It's like your initial investment. Now the 1.06, we should probably break that down as 1 plus 0.06. And then the 5 we have over here. So there's these two different things. So let's break down maybe I'll write that here. 1 plus 0.06. So we can write this in the formula as 1 plus the interest rate. Because if the interest rate was, let's say, 8%, we'd put 1 plus 0.08. Or if the interest rate was only 2%, 1 plus 0.02. And that 5, that's going to be the time. So if it's 5 years, you put a 5. If it was 10 years, you put a 10. And what this means is we now have ourselves a formula. If you're going to invest a certain amount of money at a certain interest for a certain time, we can determine how much money you'll have at the end. So sometimes we say this whole thing is equal to A. That's like the amount of money you have when all is said and done. All right, so here's our compound interest formula. A equals P, 1 plus I over N to the power of N times T. Now, everything we've talked about is the same except for the N, and so just hold off on that for a second. A is the final amount, that makes sense. P is the principal, the initial amount. I is the interest rate as a decimal. So if it was 6%, we have to divide by 100 and write that as 0.06. And T is the number of time in years. Now, N is called the number of compounding periods per year. In the last example, the interest was only compounded once a year. That means they paid you the interest every year, and so N in our last example was equal to 1. So in some ways it kind of like was irrelevant for the formula. But we could have different situations where they pay out the interest every month, every week, different compounding periods, and that will change the formula. So let's go ahead and do an example. Jimmy invests $4,000 in his savings account with a fixed rate of 6%, but we're going to compound it 4 times per year. There's 4 quarters in a year. You can think about this like every season, winter, spring, summer, fall. Jimmy gets paid out each one of those seasons. What is the account balance after 5 years? So we take our numbers, 4,000, 1 plus 0.06, divided by N, so divided by 4, to the power of 4 times 5. Now, depending on your calculator, you might have to put this part in brackets in the exponent, so just be careful with that. But go ahead and type that in, and you should get $5,387.42. Now, what's interesting about this is if you remember before, we had $5,352.90. So if you notice, the numbers are kind of the same, but the 52 is turned into an 87. So there's a little bit more money. And so if you compound something more frequently, in other words, if the interest gets paid out to you more frequently, then that means you get to make your interest on your interest sooner, and it compounds faster and you do make more money. So interesting little life advice there. But let's keep going. Jimmy's going to invest for a fixed annual interest of 7.5%, compounded 6 times a year. He wants to have $3,000 in 3 years. How much does he have to invest? So again, I'm going to put the formula here for you. A equals P, 1 plus I over N to the power of NT. And I would encourage you to pause the video and give this one a try. See if you can at least plug in all the numbers and potentially solve for the missing value. All right, so this question is a little different because we're told that Jimmy wants $3,000. So we actually have A, but we don't have P. How much he has to invest? This question mark is the principal. It's a very natural question. Jimmy's wondering, how much do I need to invest? Maybe he wants to buy a $3,000 car in 3 years, or maybe some fancy new PC. The thing is that Jimmy knows how much he needs in 3 years, but he doesn't know how much he needs to put in now. And so that's a question we can help him out with. We'll take our 7.5% and put it as 0.075. Right, we divide it by 100 to make it a decimal. The compounding period is 6 times a year, so that's going to be our N. and the time is 3 years. So times 3. Now, when we type all that in, we end up with a number next to the P. So let me go ahead and type that in. Okay. So next to the P, we're going to have 1.250577394. Now, we've talked about this before, but it's definitely important in this section. We want to keep all those decimals. So we want to divide by this number on both sides. And on your calculator, the way you can do this is you can type in 3,000 divided by ANS. ANS brings the answer. So you divide 3,000 by the answer, and it brings all the decimals on your calculator. And you should get 2398.8919 and so on. But we're going for money, and so money is a special rule in pre-cal. We just round to 2 decimal places. So you get $2398.89. So if Jimmy wants to have 3,000 in 3 years, he needs to invest 2,300, almost 2,400 now. I know this is a bit unfortunate to hear for those of you who are hoping to get rich quick. When it comes to compound interest, you really need to use time as your main method. So Jimmy thinking about 3 years isn't quite long enough for that compound interest to really do a whole lot. If Jimmy wants to have a lot of money saved, he should probably start saving earlier. If Jimmy was thinking maybe 13 years in the future, he would need a lot less to start with. All right, now we're going to continue studying this idea of compounding. So how much money would you have if you invested $1 at 100% interest compounded once per year? Okay, well, this is kind of a weird situation because you're only going to invest $1 and you're getting a crazy interest rate, 100%. But let's go ahead and crunch the numbers. So principal of $1. We do that in another color. So $1 for my principal. 1 plus, well, 100% will be 1. It's compounded once a year, so my n is 1. And then 1 times, well, it's for 1 year. Okay, that's a ton of ones. What does that give me? That's, well, I can type it in just as it stands in my calculator. 1 bracket 1 plus 1 divided by 1 to the power of 1 times 1. And I get 2. Okay, not really interesting, but let's try it again. We're going to invest $1 at 100%, but we're going to compound it twice per year. So everything's going to stay the same. 1 times 1 plus 1 divided by, but the n is going to become 2. In the exponent here, we're going to have 2 still times 1, still 1 year. So if you have this nicely set up on your calculator, you should be able to go in there and just change the number. So it's 1 plus 1 over 2 instead of 1 over 1 to the power of 2 times 1. And this will give you 2.25. Now this makes sense. If you compound it more frequently, not once a year, but twice a year, then the amount of interest you make goes up. And you might start to think, well, if I can make more money just by compounding more frequently, let's compound away. What if we compounded 12 times a year? So we'd have 1 times 1 plus 1 over 12 to the power of 12 times 1. Okay, let's see this on our calculator. Okay, you should get 2.61. All right, the numbers are going up. We had 2, now we have 2.25, now 2.61. Let's compound not just 12 times a year, not every month, but let's go 365 times. This means we're compounding every day. So we divide by 365 to the power of 365 times 1. All right, let me change this on my calculator, see what I get. I'm hoping for a big payday. This looks like compounding every day should be huge. 2.71. I mean, it is more, right? This is more. But I thought we'd be breaking 3 for sure. I thought we'd maybe be like a 350. So it's more, but maybe not as much as more as I thought. But you know what? Let's just keep going. Let's compound it more. Rather than asking for our compounding every day, let's ask for our compounding kind of like maybe every hour or something. Let's compound it 10,000 times a year. Okay, so we're just going to compound the heck out of this money. 1 times 1 plus 1 over 10,000 to the 10,000. I mean, 10,000 as a power. Oh, we should be rich here. This should be our ticket to freedom. Unlimited money. Let's go ahead and type it in and see what we get. 2.718. So I guess this would round to 2.72. All that extra compounding only got us a penny? Man, maybe we just need to compound more. Maybe we should just compound it like a million. Let's just do like a million times. Let's just compound it a million times. Okay, so 1 over 1 million to the 1 million times 1. We just probably didn't add enough zeros. Okay. Let's compound it a million times. Nope. We're still getting 2.78. Well, I mean, I thought the more we compounded, the more money we would get, but it seems like we're kind of hitting a ceiling. Even if we do compounding 10,000 times, a million times, we can't really get past 2.718. On your calculator, if you look next to the pi button, there should be another letter in red on the Mr. Peters approved calculator. So there's a pi, and there should be a little e there. You need to hit the alpha button, and if you hit alpha e, you should get 2.718 ... On your calculator, there's this E button. If you are still searching for it, maybe Google where your E button is, or come see one of your friends. Maybe just get the Mr. Peters approved calculator. But yeah, there's an E button on your calculator, and it's a special math number. Pi, if you remember, is 3.141, and so on. And pi relates to circles and radius, diameter, circumference, right? All that stuff. Well, there's another special math number, the number e. It's equal to approximately 2.718. And if you notice, that's the same number that we got here. So e is this special number that has to deal with compound interest. And it's kind of like the maximum amount that you could get from $1 if you compounded it as much as possible. Kind of a neat idea, and it's going to play a role in some of the problems we do. E is very closely related to compounding, to exponentials, and it's a neat number to know about. Until now, you've really only known about one cool math number, pi, but there's this other one, the number e. And so I want us to experiment with it a little bit. So we're going to use our calculator to find the value of the following numbers and order them from the largest to smallest, or smallest to largest, it doesn't really matter. We're going to order them up. So we're going to start with e, then find e squared, 2 to the e, pi to the e to the pi, root e, and e to the e. So you need to be able to find the e button and the pi button. Hopefully you can find them on your calculator. And let's go ahead and write them as decimals. So e is going to be approximately 2.718. E squared is 7.389. 2 to the power of e, that's kind of weird, 6.580. Pi to the power of e is 22.459. E to the power of pi is 23.141. Well, it looks like that one's a little bigger. The square root of e is 1.649, and e to the power of e is 15.6 0.154. So it looks like the smallest one here is going to be root e. The next one would be e. Then we're looking at 2 to the e squared, e to the e, pi to the e, and the biggest will be e to the pi. Now, you wouldn't necessarily have to know these, although you should know that e is approximately 2.718. That's important to know in math, just like it's important to know that pi is approximately 3.141. These are numbers that are nice to have handy. But as you'll see, we can do some different things with e that I find quite interesting. Here's one example just to start us off. We could solve an exponential equation with a base of e. Remember, we look for common base like 2 or 5 or maybe 7. Well, here we have a base e, and we can use all of our exponential rules just like normal. For example, here we're going to multiply, so we'll get e to the 8x plus 2 divided by e equals, here we'll multiply again, e, because power to a power we multiply, so 15x minus 3 times e to the 2. Now this is e to the 1, so we're going to subtract. It'll be e to the 8x plus 1, because we're going to subtract the 2 and the 1. Over here we're going to add the minus 3 and the 2, so that's going to give us e to the 15x minus 1. Negative 3 plus 2 is negative 1. Now we can drop that base, and we'll move the 8x to one side, the 1 to the other side, so 2 equals 7x, so x equals 2 over 7. And so we can do these exponential equations with a base of e. It's kind of fun, it looks kind of interesting, and it's just one of the many things that we'll be able to do with the base of e. Now we'll take some notes on this real quick. This was sort of an introduction to compound interest. And we also looked at the number e. So for compound interest, the formula is a equals p 1 plus I over n to the power of nt. But this will always be given. So you don't have to worry about the formula on a test or an exam. They'll give you the formula. But it is nice to have seen it and used it a couple times, so you kind of understand what each term represents. And there's a few little places to get tripped up, right? We have to write it as a decimal. So if you have 7.5%, you have to divide that by 100 to get 0.075. It's easy to make a mistake on the decimals on that one if you're not just going methodically. And then n, of course, is the compounding period, p is the principal, etc., etc. So for an example here, real quick, let's say you had p as 1,000, I as 6.5%, n as 3, and t as 10. Solve for a. So I'll give you a moment to give that a try. All right, so you should get 1,000. Let me do this in another color. 1,000. 1 plus 0.065 over 3 to the 3 times 10. That should give you 1902.29. So that obviously raises another thing to write down for notes, is money is 2 decimal places. So watch for that. And also I would recommend use the ands button on your calculator, so that way you avoid any rounding errors. Avoid any rounding errors. Now for some more practice, you can try Unit 8, Worksheet number 4. And then any things to remember. One thing that might be worth remembering, or even the notes, is that e is approximately 2.718. And it is a special math number, sometimes called a constant, It's very useful as we continue on in this unit. And if you take calculus later, it shows up all the time. Now, in terms of money, sometimes when I'm in class, it's nice to have a discussion. Unfortunately, in a video format, we're not really able to do that, but I would encourage you that if you have questions or you wonder about things like interest, compound interest, things like investments or ways of saving, these are the kinds of things you want to start thinking about. I would encourage you to talk with your teachers, talk with family members. You can always find some great resources as well on the internet, looking at things like, how does investing work? What age do you have to be to start looking at retirement, tax-free savings account, those kinds of things. You're never really too young. Some of the accounts you have to be 18 for, but you're never really too young to start looking at saving, investing, your retirement, those kinds of long-term financial planning. I know sometimes it feels like you're young and, those are problems for another day. But when it comes to saving and investing, it really does pay to start young. The earlier you start, the longer that interest has to work, especially the compound interest. And so, if you're about to have a summer job and you're thinking, between grade 12 and university, maybe I'll take a gap year. Looking at taking some of that money and saving it can be a really powerful first step in beginning your sort of financial goals. And so I encourage you to start thinking about that. And maybe putting some money into some different types of savings. But the specifics of all that, you kind of have to do some work. You probably have to go to a bank. You have to have some of those conversations. I can't tell you the specifics of where to invest. And of course, I don't have some magic plan to get you rich by 25. There's no real easy way to become a millionaire. But if you work at it, you put your money away and you invest, you should be all right. So hopefully you enjoyed this video. And as always, thanks for watching.